we would devise some, or we would try to find the method how to select the length and the diameter of the material, diameter of the resistance, so that we can considering that this is cylindrical material, and if the shape of that is different, you can actually calculate how we need to calculate the cross sectional area and the length of the material to be used. The
Sir,
temperature, bolo.
your recording is off.
Oh, thank you. So okay. The temperature coefficient, let's write in this alpha. The temperature coefficient should be as low as possible. Okay. Let me check again. So the temperature coefficient of the resistance should be as low as possible. Otherwise, if they are, because we are working with high temperature usually. So if the temperature changes, and due to that the resistance of the material changes, so the system may not become or remain same. So due to that, there may be different problems. So, and of course, the material should be able to withstand the temperature created by itself. Melting point should be as high as possible. So temperature coefficient as low as possible. So due to that, we have a few materials which are suitable for different ranges of temperature. I am actually taking help from a I would say list. This is not something I can remember, and also you need not or don't have to remember this. I will keep it with you handy in case you require this. So there are a few, I would say, selected suitable material which is suitable for different range of temperature. So very popular is the constant 10. So this is an alloy of copper and nickel usually, depending upon the composition of the copper and nickel, the constantan have I would say this group of material or this alloy has different properties. But the very popular material of constantan copper nickel alloy uh, has around 75% of copper and 25% of nickel. And this is suitable for usually this is up to 400 degrees centigrade. This can be used. So there are variation, and this variation can be around 55% of copper plus 45% of nickel. So for the nickel content can be increased and copper content can be reduced depending upon various values of resistances. However, these are suitable for up to usage up to 400 degrees centigrade or so. Then we have different types of chromium alloy, nickel chromium alloy. So this as such has no name. Uh, 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 However, if we put around 60% of, I am not putting a percentage here, 60% of nickel, 20 around 24 25% of iron, and rest 16%, 84, 16% of chromium that can be used up to around 950 degrees centigrade. Another type is of course the popularly known material of nichrome. So here nichrome has around
क्या
80% of nickel
क्या
and of course 20% of chromium, nickel and chromium. So this can be used
बीस
around
को मारे
1100 degrees centigrade.
मारे छुट्टी मारे
And then we have different group of material which has the composition of nickel, iron and aluminum, and that can be used of course up to 1400 degrees centigrade. And before that there is a popular group of material which is named by the known by the trade name of Kamthal. Kanthal family. So here you may have around 70% of iron, 25% chromium, and rest 5% aluminum. So of course there are variations of this, and this can be used around 1200 degrees. All those temperature figures are rough figures. And with respect to that, we can have nickel iron alloy. So this has no trade name as such. So we can have 65% nickel, 30% iron, 95 and 5% aluminum. This can be used up to 1400 degrees centigrade or so. For let's see, one second. A very popular type of material are actually the compounds which are known by their generalized property or generalized chemical structure of some metal, and let me write this way: metal into twice silicon, so metal disilicide. Okay, so these are very popular because of their usage, that those can be used at very high temperature, and they are popular for making the refractory line in when you have some sort of, let's say, furnace of course. So here we are consider all those heat producing element or electric heating when they are used at a very large scale. So they would be called the furnace, that came from the mechanical furnace name. So inside, because the temperature is very high, so furnace inside wall that should be able to withstand that sort of high temperature. So that means we need to put some sort of, not only here, there also we need to put some sort of material such that they can withstand that very high temperature. So the inside wall of the furnaces are usually used, usually made of this sort of material. So here we have once again two very popular material, namely, let's say, one is the uh, molybdenum and tungsten. They are very popular. If you consider tungsten disilicide, they can be used up to around 1000 degrees centigrade. And another is the most popular one is molybdenum disilicide. They are mainly used for the inside lining of the refractory material as the refractory material of the furnaces. They can be used up to 1800 degrees centigrade or so. Its melting point is more than around 2100 degrees centigrade, 2100 degrees centigrade or so. In this context, there is a very peculiar material known as the PTC rubber or PTC. That is the so the uh, the behavior of this material is such that it would have a low resistance. It can maintain a temperature, constant temperature up to 80 degrees centigrade, such that initially when the temperature is increased from low and this heats up, but after certain point of time, certain amount of time, the temperature it can or temperature of this would be up to 80 degrees. Temperature of this becomes to be around 80 degrees centigrade, and beyond that the temperature actually it has a resistive property such that it would make the change the resistance such that it would the current would be limited, such that it would allow the temperature range or temperature increase up to around 80 degrees centigrade or so. So, so that is called. So now about let's move on to our electrical part. These are all materials, different types of materials which are suitable for to be used as different resistive, creating the resistive element, and these are for just for the sake of mainly for the sake of I would say information. Now let's come back to our electrical part where would be mainly interested about controlling the how the heat can be controlled by using our electrical characteristics or electrical circuit elements. So now, of course, our by our known term, we know that the power delivered or power generated by a resistance is simply V square by the resistance. So that means if we want to control the power, we have two aspects we can control, either the voltage applied or we can control the resistance of the material which is there for us. So that those are the two aspects or two methods only we have, two controls we have only for changing the power that need to be controlled. So here mainly we will discuss about the open loop control. There is usually you just know that whether things should be increased or the power should be increased or decreased. These are of course not precise. Other than that, you can actually, if you want to increase, then in that case, let's say from the voltage point of view, you increase the voltage, or to reduce that, you reduce the voltage. This way, you can control the heat generated. That's all. In closed loop control, of course, we can control the temperature. Usually, the temperature is the one which we need to control. So the temperature can be once again like a closed loop control. That temperature is to be changed. So now by using some sort of PI or PID, whatever. Usually PI is very popular. However, here P control is usually I would say gives a good response for this because temperature as such is heating or this mechanical being a mechanical process that is a very slow process. So even PID sometimes also because the you can if you want to control the temperature precisely, in that case you can use PID also. So P controller by itself will be suitable. I would say is enough. Otherwise, if you go for the precision, you can do that. However, temperature is very difficult to control the temperature precisely because that being a very slow process. Anyway, so let's come back. So how first let's discuss about how can we change the or control the voltage. So if this is this AC voltage, so we can use some sort of auto transformer or some sort of auto transformer where we would be able to control the voltage very precisely depending upon the requirement. Of course, here, although we are claiming this to be an open loop system, so usually the operator's sense of the determining the temperature and with I would say experience, this becomes more and more precise. So that may that you may consider to be a closed loop system also. However, other than that, this is actually theoretically, or I would say from the electrical point of view, this is an open loop system. So if this is AC voltage, you can use an auto transformer or you can use a tap reactor system. Okay, tapped reactor, because otherwise if you use a resistance to drop the voltage, so that would be a loss, that would be lossy in nature, other because further, because the current here would be very high, so if you use a resistance here, there would be huge amount of power loss. So the efficiency of the system may become lower. Remember, although here we are finally the heat is generated, and that heat, although here should not be considered to be a loss, because the heat here generated is the form of power we are going to transform to finally. So that is the usable power, I would say. So heat is not a loss here. However, if, you may ask further that if we connect a resistance, that is also produced, that would also produce the heat. So whether that can, why should we consider that to be a loss? So the problem is that the extra resistance we have connected, that heat, if you consider that to be usable heat, or that should be utilized, so that means you are actually increasing the power that to be dissipated there, or the power that is utilized there. So that means further you cannot, or your control is not there, because in terms of the voltage you are actually utilizing the whole full voltage without dropping the heat, the power you are dissipating in the external resistance, that is also comes into a picture, because that is the heat you are also using. So that means you cannot control this way, or otherwise if you
Can you
consider
please
that.
repeat this? Sir?
Ah, if you, my point is that if you connect a resistance there to drop some voltage such that the voltage across the heating element would be lower. Okay, so you can control that way. However, that would be considered the heat produced across the, or by the external resistance, that would be considered a heat, lost heat. That is not the heat that is utilized, because if you want to utilize that, that should be considered to be internal to the system. So your voltage across the heating element comes to be V, not a variable voltage. So that should not be considered here. So if you don't want to consider that heat, that heat to be a usable heat, so that means that is the lost heat or that lost power. So that means the efficiency of the system becomes lower. So heating trapped element, tap in reactor. So that is not very new thing to you. So there may be an, let's say, an AC source. So this may be the resistance across which we are trying to generate the heat. So now from this we need to connect here. So due to that, by using the changing the tap of the inductor, we can change the variable, we can change the voltage across the resistance, heating resistance, thereby we can change the power generated. Now if you have a variable voltage supply, dedicated variable voltage supply, in case by using, let's say, generator, uh, variable supply, this can be AC or DC, whatever. Auto transformer you can use in AC only. Tapped reactor, of course, once again AC only. So variable supply, if you have the, I would say, separate variable supply, you can use that. So by changing the voltage of the supply, you can change the temperature or heat generated. We can use some sort of power electronic converter. Namely, this can be a chopper for, let's say, uh, DC-DC control. If the source is DC and you need to control the uh, so you need to control the output voltage or voltage across the heating element. In that case, by the power electronic different types of choppers, you can control buck converter or boost converter. You can control the variable voltage across the heating element. Here also you need not, the output of the chopper need not have a that need not be a closed loop structure. However, even if the output of the chopper is yeah, controlled by using a closed loop structure, that should not be considered to be a closed loop or closed, I'd say, closed loop control of the heating, because the heat is not sensed, or the temperature of the or the temperature which is the final control variable, that is not sensed, and that is not used for any closed feedback path, or that is not used as a feedback. So that means this would not still this would not be considered a closed loop system if you are using the voltage of the chopper. However, if you are sensing the temperature and that using that for the control, in that case that becomes a closed loop form. Uh, so, however, if this is of course for DC to DC, you can use chopper. So let's write this way: DC to DC, use some sort of chopper, or let's say buck boost converter. If this is an AC voltage, so here also we can control. Here comes mainly 2 points. So here there are two forms of control. One is the using some sort of track or so. One is the control. Let me draw this way. Allow me 1 second to complete the drawing. So okay. So here, depending upon the requirement, what is done is that we would use first. Okay, for the first method, we can use this sort of a structure where we would, by the known value, known I would say form of control, we can control the delay, or we can call delay the switching pulse, such that only, let's say, for this half of the shown first half of the sine wave, first positive half of the sine wave, only here we would delay the switching such that we would switch here on the blue line, and that means this much of the voltage would be applied across the load. So further, for the negative half, we can control this way. So this much of the negative half would be applied across the load. So finally, we can convert this to be a DC, or we can use the AC directly. So this would be called firing angle or triggering angle control, or these are called phase control rectifier. If the that is converted by using either ACR or the track, this is converted to DC and then used. Otherwise, we can directly use by using, or by controlling using a track, we can directly use without converting that to be DC, which we can directly control that on both sides of the positive and negative half, and thereby, because it does not matter whether you are using AC or DC for the heat generation. It depends the resistance. If there is a resistance that would produce same amount of heat given the same amount of RMS voltage across that. Okay, so we can also do the same thing without converting to DC. So that would be called phase control operation of the I would say converter. So that can be done by using an ACR, or back-to-back ACR, or trial directly. However, you see here the problem here. You can take a king from the last class or last chapter. That if we do so, the current through the, although the voltage across this applied voltage applied across the I would say system is AC, pure AC, where we have sinusoidal waveform. The current generated by the system or current drawn by the system is not pure AC. There would be harmonics generated, so that may pollute the system. So we need some method such that the harmonics are reduced from the system, or harmonics are taken into account locally, such that they does not pollute they do not pollute the power system. So to circumvent that, we can use another mechanism, another method, which is sometimes called integral cycle. This should not be called an integral cycle control. However, some people call that integral cycle control. That should not be used, I would say. So in integral cycle control, what we would do is we would allow, let's say, if we require higher amount of heat, we would allow a full cycle. Then let's say, and let's for example consider 10 such cycles are there. Now if we use 9 cycle and put the system shutdown for one cycle, then so we would have 9 by 10 amount of 9 by 10 square amount of voltage, or RMS voltage, or let's say 9 by 10 amount of heat generated. Next we can do is 8 by 10, 7 by 10 this way, and finally 0 by 10 if we turn off for a full cycle. So this way we have of course the current. However, the current or the we can reduce or we can control the voltage or control the power here. However, the current is not I would say current still remains sinusoidal. Only difficulty or only problem is that here the control is would not be that precise. That precise in the sense we can control the firing angle for the phase control system or phase control operation. We can delay the firing angle up to whatever may be required, whatever may be the requirement, and that control can be very precise. However, if you consider a let's say 10 cycles, you can only or you only have 10 possible control or 10 possible I would say control points. However, you can use let's say now you would say I can use 100 such cycles. In that case, you have 100 such control points. Of course, your system requires larger memory and or larger counter. That's all. That becomes a bit complex. However, nowadays that's not a problem. Anyway, so that those are the and this is called the sometimes called the integral cycle control. So this does not introduce any harmonics. However, because of the popularity of the availability of SCRs, low cost SCRs, so we usually use the or both of them are popular. These are usually the integral cycle control is used for lower power system where the power requirement is a bit low, and higher for higher power system the phase control operation is used. But the phase control operation has has an advantage in terms of let's say when the furnace is low, that is not running, the resistance of the due to the low temperature, the resistance value may become very low. Here, of course, we discussed about the temperature coefficient of the resistance. However, that is for the normal operation. The temperature coefficient, even if that is low, if your temperature is very low in the sense of room temperature, the resistance value, resistance is what is used inside the furnace. The resistance of them become very low. Now, once that is put in operation, that attains some heat or to the point of rated heat, so that resistance become to its rated value. There, the current itself would be limited by the resistance. However, at starting, the current may become very high because the resistance would be of the order of, I would say, few around 1 by let's say 10 times. So the current would become, if you suddenly turn on the furnace or turn on the current through the resistance, the current may be around 10 times larger. So due to that, there may be sometimes called the thermal shock. There may be problem because of the very high current. So due to that, initially for the even for the integral cycle control system also, phase control is done for the initial few cycles or at starting. Then the system moves to the integral cycle control. Okay. Okay. So that those were about the resistance control or the voltage control. Now we can also do the same thing, or we can control the heat generated by using the resistance control or changing the modifying or controlling the resistance value. So let's discuss this way. So by you can change the resistance, but however, it depends upon the situation. Usually, for the possibility or to create the provision of changing the resistance, we usually require, I would say, different extra resistances to be connected. Not extra, the total resistance is to be subdivided into parallel resistances. So now, depending upon the requirement, here I should not put an arrow because otherwise, of course, it depends upon the availability of resistance values. So depending upon the requirement, the resistance values will be connected. They may be connected in parallel, they may be connected separately, one by one after another, this way also. So depending upon the availability of the resistances, So the total resistance value apply connected across the source can be changed, and due to that, of course, the heating changes. If we have a delta or three elements, this is of course a speciality of three resistances. So if we have three such resistances, we can connect, and this is a three-phase supply. We can connect the resistances in series, and sorry, in star and delta. Now, of course, depending upon the connection, in star, if they are connected in phase, so their resistance values would become higher. So the power generated for the same voltage would be lower. And in delta, of course, the power generated by the same resistances would be higher because they are connected across the voltage source directly. Further, if we have such similar, let's say, availability of three such availability of further resistances, let's say like this. So for one phase there may be resistances connect further resistances connected. So here although this look like to be a star, I have not connected anything here. So here we have the possibility or availability such that let's say we can connect three resistance of one resistance of each phase to be star, and one resistance another set of resistance in each phase to be delta further, and another resistance
क्या
of each phase to be in star also.
आ
So
रहे
this way
हैं?
we can modify the available resistances such that we can control the total heat generated. Further, they can be the resistances by itself can be connected in parallel for the and find then made to be star or made to be delta. So this way we have different I would say arrangement of the resistances. Those can be done such that we can control the by modifying the available or resistance connection. We can control the heat generated. Now, for this, the important another important aspect is the designing the heating elements. So heating element means, of course, the resistance. Okay, so let's consider here for the time being that the resistance we are considering or the heating element would be the resist. We would connect. We would have a material, and from that usually the heat wear of the material. And here our point would be discussing. One second. Here our point would be discussing about how long or given a wear of the material, what should be the length of the material we need to take into account or we need to take such that we wound somewhere or put a material, put the material somewhere, and that would produce the required amount of heat. So, in effect, we are considering the heating element is cylindrical in nature, cylindrical in structure. So, due to that, we require that first thing is that we require the length of the material to be taken, and further for this also we require the diameter of the material to be available. Other than that, if we consider some sort of resistive element, resistive wear, in that case, either the diameter should be specified or you need to take into account the available diameter in the market, and from that you need to select the diameter that would be suitable for you, and the length. It may happen that you cannot actually afford or you cannot actually put the length of the material. Let's say the length becomes a few tens of meters. So in that case, you may not be able to put that much material for generating the heat. So in that case, you need to reduce the diameter such that probably the in that case such that the resistance become higher, and or that you need to increase the diameter such that resistance become lower, and to compensate the required length such that you can reduce or increase the length of the material. Okay. So it depends upon the total system. You just cannot actually say that this is the requirement length and this is the diameter. Of course, you need to take into account what is the mechanical structure there. So let's start. So resistance, we know that resistance of the material is rho L length divided by the area, because we consider the material to be cylindrical in shape. So this should be pi d square by 4. Let's add this pi d is the diameter divided by 4. So this becomes 4 rho L by d square. So and power generated or power dissipated by the resistive material is d square divided by r. So this becomes, oh sorry, I missed the pi here, d square pi d square divided by 4 rho into length. Let me modify that. So from this we have the information. However, we cannot take out the uh, L and D here because they are related by the same equation. So however, we can do this, that if I take the L by D square on the to the left hand side, this becomes uh, pi by 4 remains on the right hand side, d square by rho into 1 by, this remains on the right hand side. So if we have the information about the voltage and if we have the information about the voltage and the power generated, power to be generated, and of course the type of the material, from that we know what would be the value of the resistivity. So we know the ratio of L by D square. So however, we cannot take out L and D from here. Now, because here we would consider most of the heat would be dissipated or transferred uh, to the charge by mainly by radiation. So we have to use the Stephen Boltzmann law, that the power to be dissipated is the Stephen's constant, that is around 5.7 into, let's say, the efficiency, radiation efficiency, and then we have to use something called emissivity, which is one for the black body, and as the property of the material deviates from black body, this value of E reduces from 1, and finally we have the popular Stephen's law, that is, let's say, P1, which is the temperature of the resistance which is producing the heat, and raised to the power minus the temperature of the charge to which it is delivering the heat to the power 4. This unit is watt per meter square. So this is the, so that means to deliver some sort of power, some sort of wattage, we need, let's say, this much amount of wattage that would be delivered by the system, with K efficiency of the transfer being K and emissivity being E, and the amount, this much watt would be delivered per unit surface area, per unit meter square surface area, 1 meter square surface area for this. Now, of course, at steady state, the amount of power that will be delivered, because the power generated by the resistance should be completely delivered to the, because we are considering the resistance itself is the material which is delivering the power. So all the power generated by the material would be delivered by radiation. So that means we have P equals to H into the surface area, because here we are considering the that is to be cylinder. So the surface area would be pi 2 pi r or pi d into the length. So this is the total surface area of the cylinder. So this much amount of heat would be radiated, and that must be equal to the power generated by the resistance. So from here, once again, we cannot take out the L and D. So once again, we just keep into this D into L equals to P divided by pi into H. So this remains this. So here we know the temperature of the, we must know the temperature of the resistance, or if the resistance has a temperature property, in that case this should be the this T1 should be that the maximum allowable temperature is T1, and T2 of course should be known because that is the temperature of the chart that you need to create. And due to that, and from that you know what should be the amount of heat that, or amount wattage of amount of power per unit surface area that unit must deliver. So from that you know what will be D into L. Now P is known to you. So from these two equations, we can find, using these two equations, if you multiply them, P would be taken out. So from that, by using the known values, you can actually find L by D square. So or L square, that you need to just, okay, you need to square something, and or you actually divide the second equation by the first equation. So you would have D cube, and once you have d cube you can calculate d, and from that by using any one of the relationships you would be able to find what would be the value of the length. So there, this way you can actually calculate what would be the length required for the length and diameter required for the resistive element. So if you have any question up to this, we can discuss. Otherwise, we would move, not move. I would end here because this was the for the resistance setting. This concludes the indirect resistance setting. And in the last class we discussed about direct resistance setting. In the next class I will discuss about the arc heating because that would be a complete chapter. So here there will be no point in starting that. So any question regarding the last classes we can discuss. So no question. Next class, next week. Okay, next week I would require some time because this week this was not a small chapter. This was a large chapter, of course. There you actually had what I actually overlooked some part in terms of the control system. So here you have little bit of PI, and PID, which you have already studied more or less. So that's why I did not discuss. So and for the temperature control system, those are actually not that important. So that's why I actually overlooked that part. Otherwise, this well, by itself this is a good long chapter. So in the next class we will discuss about the arc heating.
Okay,
So
sir.
if you don't have any question, let's end here. Let's meet in the next class. Next class I would require some time.
Okay, sir. Thank you.